Okay, we're still in 11.2 of Barnett, and we're now going to take a look at the natural log function and its derivative. So remember that the inverse of the exponential function is what gave rise to what we call the logarithmic function. Okay, that's when b is bigger than 0, the base, and it's also different than 1. So when we introduced this back in chapter 2, we had y equals log base b of x. We said that's equivalent to x equals b to the power of y. Remember, we think of logs as powers. So if we see log base b of x, we really think to ourselves, to what power do we raise b in order to get x? And the answer is y. B to the power of y equals x. The domain was 0 to infinity for the log form and negative infinity to infinity for the exponential form. The range was negative infinity to infinity for the log and 0 to infinity for the exponential. Obviously, these are switched because these two functions are inverses. The base we'll be using in this section is the base e. So our b will always be the number e. And we remind you that ln of x, this notation means log base e of x, right? Essentially, the natural logarithm is simply the log with base e. With that in mind, we're ready to find the derivative of ln of x, and we're now ready to use the definition of derivative and the four-step process to find that formula. Okay, so later we'll extend the formula to include log base b of x for any base b. So we'll be able to calculate the derivative for any base b, not just the base e. Okay, so let f of x equal ln of x. That's for x bigger than 0. That's assumed. Then, using the four-step process, the first step is to find f of x plus h. Well, once again, replace x with x plus h. So this will be ln of x plus h. Step 2 is to find f of x plus h minus f of x. So from ln of x plus h, subtract the original function, ln of x. And by the properties of logs, since this is a difference, remember we had this property, ln of a minus ln of b is the same as ln of a over b, right? The quotient property. So we could turn this into a quotient, ln of x plus h over h. Moving on to step 3, we divide that difference by h. Okay, so here's what we get. 1 over h times ln of x plus h over x. Here, we're going to introduce an x over x multiple. So this is going to become 1 over x times x over h. Notice how these could cancel out, so I'm not really changing the problem at all. It's still 1 over h. I'm not changing the expression by introducing this x. Also, I know x is bigger than 0, so I'm not dividing by 0 here, so that's okay. Okay, now keeping that in mind, I get x over h times ln of 1 plus h over x. And it might not be intuitive to you why we're doing this yet, but you'll see in a second. Okay, now another trick I'm going to use is this is a multiple of the ln function. It's right in front of the ln of something. And another property you had was that a constant times ln of anything, right, is the same as ln of that anything to the power of c. So we're going to move this x to the h to the power of 1 plus h over x, the thing that we're taking the ln of, the input here. So overall, we're left with 1 over x times ln of 1 plus h over x to the power of xh. Now it might be starting to look a little familiar. This is why we did all this trickery here earlier on in step 3. The reason behind it is, if we let s equal to x over h, if we do that substitution, then look what we're left with. The limit, instead of being in terms of h, can now be given in terms of s, right? If h goes to 0, s goes to 0. And what do we have? We have the 1 over x, the limit as h approaches 0, of 1 plus s to the power of 1 over s. H over x gets replaced with s, x over h gets replaced with 1 over s. And that's how we get 1 plus s to the power of 1 over s. But what is that? That's 1 over x times ln of e. Remember, this limit is how we define e. So this gives us 1, ln of e is 1. 1 over x is the derivative of ln of x. Okay, so the derivative of ln of x is 1 over x. Remembering that, let's do these examples here. Find the derivatives for f of x equals 5 ln of x. Well, that will be the same as 5 times the derivative of ln of x. In other words, 5 times 1 over x, or just 5 over x. That's my derivative. How about part 2? X squared plus 3 ln of x. The derivative here will be 2x, that's the derivative of x squared, plus 3 over x, the derivative of 3 times ln of x. Okay, how about part C here, the third one? The derivative of 10 is 0, so we don't write that. The derivative of negative ln of x is negative 1 over x. That's our derivative there. Finally, for the last one, the derivative of x to the fourth is 4x cubed. Now notice, ln of x to the fourth could be written as 4 ln of x, and we're looking for the derivative of that, right? I can bring the 4 down, in other words. I can bring that down. Okay, and what is that going to give me? That's going to give me 4 over x. And that's how we get the answers. Double checking our work here, and reminding you for the last one, before taking the last derivative, rewrite f of x using the following property of logs. Ln of x to the fourth is the same as 4 ln of x. That's how we get that 4x cubed minus 4 over x. That's how we got that answer. Okay, so why don't we take a look at other logs and exponential functions? Well, logs and exponential functions with bases other than e may also be differentiated. For example, you could take the derivatives of log base b of x, and the answer will be 1 over ln of b times 1 over x. So this 1 over ln of b factor is introduced to balance out the different base. If you have the derivative of b, any b to the power of x, that is b to the x ln of b. Alright, so keeping that in mind, those two rules, here they are written here. Why don't we try these out? So what's the derivative of log base 5 of x? Well, according to this rule, this should be 1 over the ln of the base, which is 5, times 1 over x. How about the derivative of 2 to the x minus 3 to the x? Okay, well, using the second rule, the derivative of 2 to the x is 2 to the x times the natural log of 2. From that, I subtract the derivative of 3 to the x. That's just 3 to the x times the natural log of 3. What's the derivative of log base 5 of x to the fourth? Well, once again, we could use that nice property of logarithms that says this is equivalent to 4 log base 5 of x. And now when we take the derivative, we see that this is really 4 times the derivative of log base 5 of x. And log base 5 of x, we found the derivative in the very first example here. That was 1 over ln of 5 times 1 over x. So this derivative is really 4 over ln of 5 times 1 over x. Let's double check our work here. And it seems like we're getting these all right. And that's that. So to summarize, here is the exponential and log rule. And here are the derivatives for any base to the x power and for log of any base b of x. So remember those. We're going to use them quite frequently. In fact, one of the application of them is given in this problem. Let's do it together. On a national tour of a rock band, the demand for t-shirts is given by this formula. P of x equals 10 times 0.9608 to the power of x, where x is the number of t-shirts in thousands that can be sold during a single concert at a price of $P. The first question says find the production level that produces the maximum revenue and then find the maximum revenue itself. Well, to do that, remember, revenue is the number of items produced times P of x, right? So this is the price function in this case, or the demand function, whatever it is you have. We have the demand function, P of x. We multiply that by x, which is the production level, the number of t-shirts that can be sold. And we obtain our new function, 10x times 0.9608 to the power of x. Then, to figure out what the maximum is, we graph on our calculator and we find the maximum. So to do this on my calculator here, I have preset the window to the following. After playing around with the graph a bit, I decided this is the best window. X min is 0, X max is 30, the X scale I put is 2, Y min is 0, Y max is 110, and Y scale is 10. So then I typed in my function. Here it is if you haven't typed it into yours. 10x times 0.9608 to the power of x. And the screen cuts off here a little, but you could see it, 0.9608 to the power of x. And when I graph that, I can see the maximum point right about here somewhere, right, as I point to it, right about here. So what I do to figure out what that is I use second, calc, and option 4, maximum. That's going to get me very close to the maximum value. The calculator is going to ask for a left and a right bound. Those are numbers to the left and to the right of the maximum. That number is good enough. I could hit enter to say, yeah, that's a left bound. Then I'm going to try and scroll using the right arrow key all the way to the right of this maximum value, right? So I'm not there yet. The maximum is somewhere around here, it seems like. So I'm going to go a few more pixels to the right where I'm below that point, like over there, for example. See, I even move the screen a little bit to get a better view. So I can select that as the right bound. Then the calculator asked me to take a guess. I could just hit enter instead, and it's going to spit out a maximum value. So it's at about 25 t-shirts. We're going to get a maximum value of about 92 or 91.99, right? 92. So going back to our slides, this calculator displayed a little bit of a different answer, but it doesn't matter. It's all the same pretty much. So it seems like the maximum will be about $92, and it will happen at 25 t-shirts. That will be the maximum revenue. Okay, question 2 says, find the rate of change of price with respect to demand. Well, rate of change is a fancy way of saying derivative, right? We saw that in chapter 10 when we defined the derivative. And not only do we want to find the rate of change, or the derivative of price, with respect to demand, we want to do so when demand is 25,000. To solve that, all we do is take the derivative p prime of x of our expression. The work is done here on the screen, and then we substitute 25 in for x. So what does the derivative of negative 0.147 tell us? It tells us that when demand is 25,000 shirts, in order to sell an additional 1,000, the price needs to drop 15 cents, because this is negative, right? And p was measured in thousands of shirts. So by the interpretation of the derivative, to sell the 26,000 shirts, we need to drop the price by 15 cents. That's what this is telling us.